Hi, everyone. We've been talking about state changes. Remember, state of matter is how matter is being portrayed at any given point in space and time. And matter is anything that has mass and takes up space, right? So in this case, this little blue ball has a very famous story in our family, and it is the blue ball that goes on the sky, which the ceiling, as we call it with the kiddos. So it's the blue ball that lives in the sky. And when we lived in our old house, one day, I don't know why, we took it and we threw it up into the ceiling, and it stuck to the ceiling. And then when we moved, it was the last thing that we grabbed on the way out of our house, of our old house. So when we moved here, we are still trying to find the right spot for it. But as you can see, it's kind of a squishy ball. I think we got it at a Mexican restaurant or something, like in one of those little plastic things, like 25 cents. I'm not sure where it came from, but it's a very special little thing. And it's not really solid. It's not really a liquid in some ways. I mean, it is a solid. It's not really gaseous, but in this particular place in space and time, it is in this state of matter. So if we were to melt this thing, it would change state. It would still be the little blue ball in the sky, but it would have a different state of matter. So today I just wanted to go over a couple of terms with you that we've been talking about, and make sure that you understand them. So to make this thing change its state of matter, we would have to apply temperature, right? So we would heat it up or cool it down. You could cool it down and make it like a really frozen blue ball if you had some liquid nitrogen or something to make it really, really cold. Or we could heat it up and make it into a liquid or even a gas if it got hot enough, because I'm guessing it's some kind of like a rubber compound, not rubber, but some sort of a plastic compound that makes this thing up. So temperature is the average amount of kinetic energy within an object. So you take all the particles of an object, including the little blue ball in the sky, you take all the kinetic energy in this object, because things are moving in here. It doesn't look like it, but they are. The little atoms are constantly moving inside of you and our little blue ball in the sky. Take all the kinetic energy and you average it out, just like you do your history grade or your science grade or your math grade or your English grade. And that is the temperature. So we assign things like Fahrenheit and Celsius scales to these two temperatures, but in general, temperature is an average of all the kinetic energy in a substance, whereas thermal energy is the total amount of energy in that substance. So if we could add up all the atoms and all the thermal energies inside the blue ball in the sky, we could find the thermal energy of this thing. And there are ways to do that, and we're going to talk about that in the next chapter. But just want to make sure that you get that distinction. Thermal energy, temperature, two very different things. Similar, related, but very different, because temperature is an average, thermal energy is the total. So when we talk about these changes of states of matter, we throw around words like melting and boiling. So I want to go through those and make sure that you all understand what I mean by those when we talk about this in a scientific context. So here is our textbook, and I'm going to have that link down in our Google Classroom page. And just to make you abundantly aware, our word melting here, I'm going to highlight it. Melting, when the temperature of most solids increase, the solids change to liquid. So of course, when a solid changes to a liquid, it melts. So think of ice, melts into a liquid that we know is liquid water, as we say in Mullins. In pure crystalline solid, melting occurs at a specific temperature called the melting point. And we'll talk about what this word means, crystalline solids. We'll talk about that in class. It's very interesting. Different than amorphous solids. This is an amorphous solid, whereas the glass on my iPhone is a crystal or crystalline solid. And you can kind of think of the difference there just by hearing those two words, right? Crystalline, a lot of structure. Amorphous, very squishy, not a lot of real structure to it. Melting points, and that's the temperature, the average kinetic energy, that when something like an ice cube melts. Because an ice cube also is an example of a crystalline solid. So we'll talk about that in class tomorrow a little bit more. But we have this wonderful graph here that we started today. And if you look at the temperature here on the y-axis and time on the x-axis, so if you take a ice cube out of the freezer, it stays solid for a little while until it starts to melt at 0 degrees Celsius, which is about 32 degrees Fahrenheit. And as it melts, it still stays kind of this weird solid liquid thing. And you've seen that with an ice cube. And then all of a sudden, it gets to a point, in this case, about 12 minutes, where melting completes. So you can try this at home. If you take an ice cube out, put it on something that's not going to let your countertop get wet. But if you take an ice cube out of the freezer and you put it down, it takes about 12 minutes for it to completely melt into a liquid. And then the temperature continues to rise in a positive slope, positive rise over run. So in this case, by 16 minutes, the temperature now is about 30 degrees Celsius. And this would be if you have something heating it up or adding energy to it. If you're at room temperature, it's going to stay, and you're going to reach another plateau right around in here. But if you keep adding energy, you're going to continually increase the slope of this curve. So every substance kind of has a similar melting graph here, whether it's silver or gold or ice, it doesn't matter. It's kind of cool. They all have different temperatures at which they melt, but these graphs are really handy, and we're going to look at the freezing graph in a second. So melting graphs, typically temperature on the y-axis, time over here on the x-axis, and you have a positive slope. And this general area here is when this change of state occurs. Okay, so let's flip over to the next page. And we have freezing. So just like melting point, when a solid changes to a liquid, freezing is a change of state from a liquid to a solid. So it's the reverse of melting, obviously. And a substance's freezing point is simply the temperature at which it changes from a liquid to a solid. Not when it begins to change, but when it does change. So water's freezing point is 0 degrees Celsius. And there's some types of wax that have a much higher freezing point, much lower freezing point. You can freeze Coca-Cola, you can freeze Lysol wipes, you can freeze the blue ball in the sky. You can even freeze an iPhone. So most solids do have a freezing point because of their liquid state. So if you were to melt this thing down, you could refreeze it and make another solid out of it. So if we look at our graph here in this math section, don't worry about this stuff yet, you see we have a different type of slope. So instead of having a positive slope, temperature on the y-axis, time on the x-axis, we actually have a negative slope in changing a liquid into a solid. So key thing I want you to get, changing a solid into a liquid, positive slope, changing a liquid into a solid, or freezing, negative slope. So as we start here, we have a high temperature that gradually decreases, and we still have that weird intermediary period where things are liquid and solid. Pretty cool. Next up, we have the changes of states between liquid and gas. So that's solids and liquids, melting, freezing. Liquids and gas, a little more complicated because of how the particles are arranged in these objects. So with liquids and gases, you have evaporation and boiling. So the change of state from a liquid to a gas is called vaporization. So the change of state from a liquid to a gas, highlight that, is called vaporization. Vaporization occurs when the particles of a liquid gain enough energy to move independently away from each other. And there are two ways that we have vaporization: boiling and evaporation. So that's going to definitely be something that you need to know. Two main types of vaporization: boiling and evaporation. So you've talked about evaporation a lot, 5th grade, 6th grade. You know what evaporation means. You're in 8th grade. You know everything, right? You know what evaporation means totally. So in this case, the boiling point of a liquid is the point at which a liquid boils. So water at sea level is 100 degrees Celsius or 212 degrees Fahrenheit. Just like its melting point, its freezing point, the point at which water becomes a solid is 0 degrees Celsius or 32 degrees Fahrenheit. In this case, boiling is 100 degrees or 212 degrees Fahrenheit. That's why we should use Celsius. It's so much easier. 0 to 100. There you go. Evaporation, on the other hand, is a little different. So in this case, the book talks about a puddle, as we'll discuss. But vaporization that occurs only on the surface of a liquid is called evaporation. I'll say evaporization. Evaporation. So vaporization, when a liquid changes to a gas that occurs only on the surface of a liquid, is called evaporation. So think of a puddle. I like to think of things like Lake Murray or Lake Marion. We used to go to Lake Murray a whole lot when we lived in Columbia, and you could see evaporation from the surface of the lake, in terms of how the lake would kind of ebb and flow in its height. And when water evaporates from the surface of the ocean or a lake or a puddle, that's evaporation, because it's just at the surface. It's not the whole body of water, in this case. So you've got two types of vaporization: boiling and evaporation. All right? I think it makes sense. So there's some activities down here which we're going to look at in class. Is this boiling, or is this evaporation, or both? So in this case, we've got boiling going on in the coffee pot or the teapot, where the water is being boiled. And then here we have two footprints. I was going to say feet prints. Two footprints on the deck of a pool. Hot summer day. The person is jumping into the pool probably, or they've stood up on the side of the pool. Is that boiling, evaporation, or both? In this case, it would be evaporation, right? The surface liquid is being vaporized. And here we have a pot of what looks like spaghetti or some types of food being boiled. I don't know. But we'll pretend like it is, what should we say? I don't know. We'll pretend like it's some sort of a stew. You've got boiling, but you also have evaporation, because the water is evaporating off the top of this boiling pot of food. And we'll look at some more examples as we do our holiday feast in the next few days. So the effective pressure, I asked you to make sure you found the formula for pressure, and P equals F over A, which makes sense. So I've got blue ball in the sky. I'm going to add pressure to it. Exerting a force in newtons, which is work over distance, in a certain area. So in this case, the area of the blue ball. And if I know how much force I'm squeezing it, you can actually find the pressure. So it's not hard. And this is how we do everything from tire pressure, air pressure in our tires, to air pressure outside, how many particles are pushing on us from the atmosphere. So when you push on an object, you apply pressure to the object. The pressure depends on the force you apply over the amount of area that you're applying it. So if I push down this table, or if I push on this mouse pad, the amount of force I'm exerting in a specific area is the amount of pressure we have. So in this case, the air that surrounds you is constantly applying pressure to you. If it didn't, we would just be blobs, kind of like in WALL-E. No, yes, WALL-E, when they're all floating in space in the little chairs. Atmospheric pressure can affect how easily a liquid changes to a gas. So here's our note here. This pressure, called atmospheric pressure, can easily, let me get the whole thing. Go away. All right, this pressure, called atmospheric pressure, can easily affect how a liquid changes to a gas. So I'm going to highlight that in green because it's important. This says think about boiling water to make pasta. We'll talk about that tomorrow when we actually do some of that. But in locations high above sea level, like in Denver, the atmospheric pressure is less because the air is less dense, because it's farther away from the Earth's center. So there's fewer particles of air actually in Denver. So things like long-range runners go to Denver or even to Asheville to train, and then they come back to Columbia or to Sumter, and they're able to run long distances a little easier because they have been training in areas where the atmospheric pressure is a little less, so there's less oxygen even. This means that it takes less thermal energy to get a liquid to boil in these locations. So in Denver, water boils at 95 degrees Celsius, not 100, so 5 degrees cooler. That's pretty cool. I think it's pretty neat. So here's a little graph here of two substances. And the question is, which image shows a liquid that would require more thermal energy to change to a gas? So we've got lots of thermal energy. We've got a little less thermal energy here. So we'll look at this in class as well. And then last is condensation. And we have been talking about this, again, 4th grade, 5th grade, 6th grade. You know what condensation means. It's the reverse of vaporization. So instead of a liquid changing to a gas, it's a gas changing to a liquid. So when it's really cold, like maybe tomorrow morning, it's going to be a little chilly. You get in your car, you might have some condensation where a gas, in this case oxygen in the atmosphere, has changed to a liquid, and the H2O, the water vapor, and the hydrogen and the oxygen in the atmosphere have actually clung onto the surface of your windshield in the morning, and they have condensed, as we call it, into water vapor on your windshield, liquid water. It's pretty cool. So condensation occurs all the time. I'll show you tomorrow when I make my coffee in my black mug. If I put my hand on top and I lift my hand up, there's water vapor that has condensed into liquid water on the bottom of my hand because of the thermal energy being expressed. And there's enough thermal energy to change the state of that gas into a liquid. So it's pretty neat. And one of the fun ways to do it, of course, is to, take your hot breath, blow it on like a window, and as the lady here is doing, making a Taylor Swift heart. So fog is a common example of condensation, and clouds. They're both ways that we express condensation. And changing state from solid to gas actually happens. So think about that, a solid to a gas. And we call it sublimation. A sublimation occurs when the surface particles of a solid gain enough energy that they form a gas. Now, this is less common in our everyday life than something like evaporation or vaporization or melting or boiling, but it does happen. One example of sublimation occurs with dry ice, which we're going to look at when we come back from Thanksgiving. I'm very excited. I always love playing with dry ice. And dry ice is just solid CO2 or carbon dioxide. And at ordinary atmospheric pressures, carbon dioxide doesn't really work as a liquid, and we'll talk about why, because of its formation. So instead of melting, solid carbon dioxide, like as a frozen block of ice, changes directly to a gas. So it melts as a gas, not as a liquid. It does a little bit of liquid, but it melts as a gas. It's really cool. And we're going to look at that when we come back from Thanksgiving. And as carbon dioxide sublimes, it absorbs thermal energy from its surroundings. So we're going to talk about that. So for instance, we used to get Blue Apron all the time, and now we get like some kind of fish thing from Alaska, and they always ship with dry ice in these little packets that sublimate over time, and you can recycle them. It's pretty cool because basically the frozen carbon dioxide becomes gas, not a liquid. So we'll look at some of those as well. I've saved a couple of those packets. So we're going to look at dry ice, and that's it. So we've got sublimation, vaporization, we've got melting and boiling, and we've got our changes of state. Remember that thermal energy is behind all of this, and temperature helps out as well. But the state of matter that something is in has to completely do with the amount of energy that particle or that substance is holding or possesses, and that can change back and forth. So things that are liquid can change to gas, they can change to solids, and there's a constant cycle because matter is neither created nor destroyed, nor is energy, because they're the same thing. And blue ball in the sky will one day be recycled into something else, who knows what, and that's the mystery of the universe as we all get to participate in it. It's pretty cool. So I'm going to link the textbook section here. Take some notes if you like. Hope this helps, and I can't wait to play with some dry ice and do some other fun examples and demonstrations with you in class soon.